Well, first of all, thank you for tuning into this presentation. I will be giving a brief overview of NASA's current exoplanet discovery mission, namely TESS, the Transiting Exoplanet Survey Satellite, as well as the reasons why ground-based observers are needed to supplement this mission. Finally, I will be discussing the contributions of the AAVSO to the success of TESS. And this presentation, of course, accompanies the paper in the SAS proceedings. Unlike Kepler, which explored only a small slice of the sky, TESS was designed to do an all-sky survey in search of exoplanets around nearby M-type stars, which are the most common stars, in fact, in the galaxy. And as the name implies, TESS uses the transit method to detect an exoplanet candidate by looking for a periodic dip in the light of a target star. TESS was launched in April 2018. It completed its initial 2-year mission and is halfway through another 2-year extended mission. One of the main science objectives of TESS is to identify candidates whose atmospheres can be studied for biosignatures by the soon-to-be-launched James Webb Space Telescope. TESS has 4 onboard cameras that simultaneously are viewing one of 13 sectors in each celestial hemisphere, as you see depicted in this picture. So in 12 months, TESS can complete a survey of each hemisphere, and in 2 years, the entire celestial sphere. As I said, TESS uses the tried and true transit method, namely detecting a dip in light of a planet that happens to pass in front of its host star from our line of sight. The amount of dip and the shape of the light curve tells us, in fact, a lot about the planet, from its radius to the size of its orbit. However, in order to do an all-sky survey, the pixels on each camera are quite large, resulting in an image scale of 21 arc seconds per pixel, as compared, for example, to a typical ground-based imaging camera of, say, 1/2 to 2 arc seconds per pixel. This means that the light from the target and some of its neighbor stars could potentially be blended together. And this then raises the possibility that a dip in light detected by TESS might actually be caused by the target's neighbor. And it's for this reason, before a planet candidate can be confirmed, that it must pass through a series of gates in the TESS pipeline. The first such gate, and the one that this paper accompanying this presentation will focus on, are observations conducted by ground-based observers, many of whom are amateur astronomers with modest-sized telescopes. Even though these observations are seeing limited, they're actually able to better resolve a target from its neighbors, again, due to TESS's large pixel size and photometric aperture. What's shown here are examples of false positive cases that TESS ground-based observers are often asked to look for. The most common is case 4, where a neighbor of the target is a so-called nearby eclipsing binary, or NEB. If the magnitude difference between the NEB and the target is within a certain range, and the drop in light caused by the NEB is just right, then the blended light of the target and the NEB could in fact mimic a valid exoplanet transit. So since they can resolve the target from a close-in neighbor better than TESS can, ground-based observers are often asked to, quote, clear the field of any possible NEBs that could cause a false detect if no obvious detection was seen on the target itself. It turns out that there's a direct relationship among first of all, the depth of a TESS detected event. Secondly, the depth of an NEB event needed to mimic the TESS detected event. And third, the difference in magnitude between the target and the NEB. So in attempting to, quote, clear the field of NEBs, we use these relationships to first identify which stars could potentially be NEBs, and then for each one, see if it exhibits a dip consistent with one that could mimic the TESS detection. This picture is a sample field of some 91 stars from a recent TESS observation that shows all of the stars within 2.5 arc minutes of the target that need to be checked to see if any of them are experiencing an event that can mimic the TESS detection. In order to automate this checking, we developed for the rest of the TESS team an add-on to AstroImage-J to do this automatically. AstroImage-J is the data reduction and model fit software used by most of the TESS team. Automating this NEB checking process has saved countless hours over the manual checks that were being done previously. So how has the AAVSO helped the TESS mission? Well, even before TESS launch, we developed a process to qualify AAVSO members to be official participants in the TESS science team's ground-based follow-up group. In fact, to date, over 24 AAVSO members have joined the TESS team. We also developed the guidelines used by the entire TESS team for analyzing observations and submitting the results. We developed the automated process I alluded to earlier for clearing a target's field of potential NEBs. We also helped with the analysis of observations done remotely at the LCO observatories around the world. And finally, we have provided mentoring to both AAVSO and non-AAVSO TESS members. So I hope this presentation and the accompanying paper give you an appreciation for the challenges involved in confirming an exoplanet, as well as the contribution by the AAVSO in the success of TESS. Thank you, and clear skies.